What is the electron configuration for iron with 26 protons, symbol Fe? Now, the normal way we talk about electron configurations is what's called the strict aufbau filling rules. Aufbau being the German word for filling, okay? And that consists of sets of abstract numbers in this grid here of 2, 6, 10, 14, always even numbers, building in this diagonal pattern. So the first shell has 2, the second shell has 2 then 6, the third shell 2 and 6, and the fourth shell has 2, then 10, and then 6, and so on. Now, this filling has a set of rules. They're abstract, numeric rules, okay? First, no partials are allowed. That is, any of those shells, until you get to the next one, you just fill up a shell until you get that one full, then move to the next one, step by step. Further, there's a fill order once you get onto one of those diagonal lines here. That order is the 2 subshell S, then the 14 subshell F, then the 10 subshell D, and then the 6 subshell P. And finally, the dash Ds fill with N, but strangely enough, the energy is N minus 1. So they're presented at a lower number. And the F subshells are filled with N, but the energy is actually N minus 2. Now, these are all abstract. Now, let me explain this in a 3D model. Now, my method, Arno's, is a 3-vector, 2 hemispheres based upon the field acceleration physics stack. Now, in this way, there is 2 hemispheres, and I'm only showing here the lower hemispheres. There's a matching one above. Along the poles, you get 1, 1, 1, 1, with a matching 1, 1, 1 going the other way. Thereby, that's 1 times 2 hemispheres equals 2 electrons. Those are all the subshell ones. And then you build 3, 5, 7 in interlaced shells going this way for as much as you can fit effectively based upon these rules. So what are the rules? These are 3D engineering rules. First, there's 2 hemispheres. Second, only full subshells are allowed. There are no partials. Now this follows the math of Bose's cylinder surface from a 1924 paper, for which is what started getting him the Nobel Peace Prize. Fourth, there is a transitional equatorial subshell. Now that doesn't have 2 hemispheres because it's on the equator, and that's always an odd count of 3. And this is how you do all of the odd count electrons, because when there's an odd count, they can have a full subshell that is only 3, thereby odd, and that will provide your electron configuration exceptions. And finally, the preferred order is to fill from the pole towards the equator, but only in the tightest fit where you actually get all of these full. Let's see how that works for our target. So the electron configuration for iron, 26 protons, symbol Fe. Strict aufbau would say that this is 4s 2 in subshell S. And it would say in the subshell 3D that you have partial filling of 6 of 10. Abstract. Wikipedia says that this is not an exception. It's an even count. So those are typically not exceptions to the aufbau filling rule. However, when you do it with my thing, you can have all full subshells. And that's by filling it up with 2 at the poles, 4 subshell S2, and 4 subshell P6. It is not a partial, but that. And those are all full. Now I use a system, the Arno-Diagram, instead of the Lewis diagram to explain subshells bonding, and it helps a lot because it has a lot of 3D eyes underlying it. In this way, you fill in only full subshells until you get a count that matches. In this case, 1 plus 3 plus 3 over here. Notice that they're at offset by 1/2 phase so that each electron has its Pauli pair at 180 degrees versus the nucleus. And then another 3, 1, 3, 3, 1, 6 outer subshells. And this is using the Arno-Diagram template for shell 4 or shell 5. Now, why do I think that this works better than the strict aufbau? Let's see how that figures for chemical properties. Because in part, this 3D geometry actually tells you some of the important chemical properties of atoms. So for example, when you have a whole bunch of things down here at the end cap, the magnetic fields of these, which are trying to point here, are aligned with the nucleus. The S subshell are aligned, and these P subshells are pretty well aligned too. So when you have P subshells full, you get aligned magnetism, permanent magnets, and this is an iron, which guess what, has permanent magnetism. And 2, it blocks conductivity. That is the exact opposite of those that fill at the electron equatorial. That one, if pointing towards there, is actually perpendicular to this. So this interferes with magnetism. But look at those electrons. They can flow in and out, no problem. Where these will come and bump into inner layers or bump into these, there's not as free a space. So anything with the equatorial 3 has more electrical conductivity, and 2 blocks magnetism. And for iron, those are the properties that we know. It is permanent magnet, not good electrical conductivity. As such, that's part of the evidence of why my plan for this electrical configuration versus this one, which would be not aligned and not particularly magnetic. Wikipedia and Aufbau are wrong. Thank you.